Hi there, this is another lesson in Year 12 Discrete Maths for further maths, and we've already looked at algorithms, and this is now exercise 3B, comparing algorithms, and sometimes this is called time and order, and it essentially is us looking to see how good different algorithms are and comparing them to each other. So it might be we've got two different ways to sort a bunch of numbers, and we're trying to decide which of the two ways are the quickest, the most efficient, some people say. So we just have a look then at this. Now, time and order then, it generally looks for what we would describe as the worst case scenario. So take my example there. If I was or put in some numbers in order, I could get like numbers are 2, 5, 3, 7, 10. And you can see I've got a bit of work to do, but they're not in bad order already. So, I mean, more or less, you look at that and you think we're almost there. Or I could get the numbers 10, 7, 5, 3, 2, and they're completely in the wrong order. And probably you'd suspect that even though they're the same bunch of numbers, this one would take longer to put in order compared to the first one. Just by the first one was by fluke almost in the right order already. Assuming we wanted it in increasing order. So allowing for the fact that we're not really sure which version of the set of numbers we're going to get, we might be lucky, we might be unlucky, we look at the maximum runtime that we might end up having to use in order to for an algorithm to apply. I should point out that when we're doing this in a bit, we're going to need to know these results. And particularly, I would suggest this first one. So this result here says 1 plus 2. Now, these are actually called the triangular numbers. And the triangular numbers have a formula. And it turns out that these triangular numbers, which I've very badly written there, look, the first triangular number is number 1. And then if I add 2 to it, as this suggests here, 1 plus 2 is 3. So my next triangular number is 3. And if that was 1 plus 2, the next one would be 1 plus 2 plus 3. And if 1 plus 2 plus 3 is 6. And you keep on going. 1 plus 2 plus 3 plus 4 is 10. Now, this goes on forever and ever. I don't intend to write them all down, but you'll notice it suggests there is a formula for this. And this formula can be very, very useful. And I would say the results then are, for this, you can jump and find this 10 straight away. One way of doing it is just say, well, I want the fourth triangular number. That one there, for instance. So I'm going to do a half of 4 times 5, as suggested by this formula, half n plus 1. 4, 5 to 20, half of that is 10. So you see it kind of does work. It does give me the triangular numbers. It doesn't just work for that one, it works for all of them. I wouldn't worry about the other one quite so much. But now there's a reason for this, and it's to do with the example I've got for you. It says how many additions and multiplications are used in evaluating the cubic polynomial this. So and it even suggests a number I could slide into it. It suggests x equals 23. It doesn't have to be 23. It could be 8 or 4 or whatever. But if I was to do, for instance, this when x is 23, I think I'd have to do 4 times. Now it says cube, 23 cubed, so presumably, but cube means times it by itself, times it by itself. So you can see lots of multiplications. This is plus 5 times, well, x squared, so 23 squared. 23 times 23, what's that? Plus 6 times 23. You can see, although this says minus 7, we treat that to be like another addition. It's almost like you added on a negative number. So how many multiplications have I got? So multiplications, I've got 1, 2, 3, 4, 5, 6. And how many additions have I got? Well, I've got 1, 2, 3. So additions was 3. So it kind of implies, well, bear in mind, this is a cubic. So this is of, order 3 or degree 3, depending on how you want to describe it. So, but with my cubic polynomial, I had 6 multiplications plus 3 additions. Now the question then says, well, what if we had a multiplication with m and a for the additions and multiplications? What is a maximum runtime for evaluating a polynomial of degree n? So look, they're basically saying, look, this was a cubic, but what if it wasn't a cubic? What if it was a linear? A linear expression of degree 1 would be, for instance, 3x plus 2, something like that. You'll notice it's just got one power 1. And if I did this, what would it have? It would be 3 times a number. Let's imagine it was at 23 again, plus 2. And you can see I've got one of each. 1 multiplication and 1 addition. Now, if it was, say, quadratic, you get, say, 5x squared plus 7x minus 4. Well, that's 5 times the 23 times the 23 plus 7 times the 23, well, minus 4. Now, you quickly realize there's 1, 2, 3 multiplications now. And there are, well, what's that? 1, 2 additions. And I'm starting to think, hang on a bit, this is no fluke. I had 1, then I had 3. 1 and 3. These are less interesting. I suppose that was just 1 and that was 2. And what it turns out actually is when you do it for a polynomial of degree n, you can almost say to yourself, I'm going to have that many additions, because you can see the triangular numbers are coming out of this already. Because we, on the cubic one, we had 6, so we had 1, 3, then 6, and that's the triangular numbers. These are less interesting. Oh, I've done the wrong one there. 1, 3, and 6. The n number, the additions, is just 1, 2, and then we had 3, so that's a bit boring. But what it implies to me is that the time that you need to do it for would be probably something like, well, this horrible thing, a half of n plus 1 times the multiplications, plus probably just n lots of additions. I'll write that with a lowercase a because I just realized I was halfway through it and I'm not going to get a uppercase a. So look, I don't think it's a very nice formula, but that's what they wanted us to do. And under there, I'm sure it says it. Time and order of an algorithm then. Notice if it is linear, we often just write that as order n. And basically, as a problem increases in size, its time increases by the same scale factor. But that's not always the case. Quite the opposite, actually. Very often you find that as a problem increases, its complexity increases by more than just the size of you've increased it by. So you might, for instance, double the number of numbers, but it doesn't double the number of time it takes to sort those numbers. It might times it by 4, for instance, and that would be a quadratic order. And you can have a cubic order as well, and where it's cubed as well. We'll see those in action now. So it says an algorithm is of quadratic order. It takes 5 seconds to process. I always like to write n and t. So it's got 5 seconds to process 8 items. So there's 8 items, and it takes 5 seconds to do it. How long will it take to process 24? Well, 24, you can see that has been times by 3. But it is of quadratic order, and this is the critical thing here. So therefore, we're going to times the time by 3 squared. And 3 squared is 9, so basically 45 seconds. That's how long it takes. And notice that came about because they told me it was of quadratic order. I found out what I've done to the number of items I had. I went from 8 to 24, which was times by 3, and this is there. 3 squared, because quadratic. Do a similar one. I'll write n and t. What does it say? It's cubic order now. It's able to process 5 items in 12 seconds. How many oh, that's in the backward one. I want this one this time. How many items will be able to process in 100 seconds? Well, definitely backwards. So what has happened to go from 12 to 100? And I have no idea. It's not a very nice number, I'm sure. I'm going to do 100 divided by 12. And that says I've times by a rather horrible. Well, I'll do it as a fraction. It's better as a fraction. 25 over 3. And what that means is, see, because it's of cubic order, whatever this was has been cubed to get to this one. And so in actual fact, I'm going to have to do the cube root of 25 over 3. Let's do that now. I'm going to cube root that. Hopefully I've done that right. And I've got 2, not very nice, 2.027. So that basically means the number of numbers I could do is times by 2.027. 2.027. And if I times it by my 5, I'm going to get 10.14. Now, presumably I can't process 10.14 items, so presumably my answer is actually 10. I'm not sure if I've got the answers on this. 45 seconds and 10 items, yeah. So that makes sense. Now we've got similar ones here, a little exercise. You're welcome to pause this and watch me afterwards, but I'm just going to do it anyway. It's quadratic. Takes, okay, I just do n and t every time. It takes that long to do 10 numbers, 0.005. Find the length of time it would take to do 200 numbers. So very quickly you say, well, that's been times by 20. And if that's the case, what is it? It's quadratic order. Oh, that's just going to be times by 20 squared then. Again, you look at quadratic, you think 20 squared. So 20 squared is 400 times by that 0.005. And that just gives me 2 seconds to do that. Algorithm B is of cubic order. I'll just write n and t again. It takes algorithm 0.25 seconds to sort 5 numbers. So 5 is 0.25. How long will it take to do 30 numbers? So I quickly think to myself, oh, that's times by 6. Now it's cubic order here, so it's times 6 cubed. 6 cubed times by the 0.25, 54. 54 seconds. And then it looks like I've got a backward one. So I'm going to write n and t again. I know it's 5 and 0.25. And it says, find the size of the list required that I could do in 2 seconds. I see. So that has been times by 8. Quickly doing them ahead. It's cubic order, so I'm going to do the cube root of 8. Cube root of 8 equals 2. Oh, I can't believe I just did that on my calculator. And so therefore this presumably is times by 2, which is 10. Algorithm D takes, again, n and t. It's 6 numbers in 0.425. It's cubic order again. Find the length of time it would take to... This is another backward one. No, it's not. It's 48. I thought it was going to be a backward one, but it's not. That's times by 8. So this is times by 8 cubed. So 0.425 times 8 cubed equals, what's that? 217.6 seconds. Now, I'm not sure if they're right. 217 is, 10 is right, 54 is right, and 2 is right. And then there's a couple more, which I'm going to actually leave these for you to do. And here are my numbers, my answers, rather. And according to me, those are them. So I'm going to leave you to work out and see if you can agree with those. Just to finish with now, a couple of last things. And we mentioned this right at the start. We started off by saying that we had this function, which was 4x cubed plus 5x squared plus 6x minus 7. I think those are the same ones we started with. Otherwise, it doesn't really matter. But I'm saying to you, look, you can rewrite this. And you can rewrite this in this alternate form. Now, you don't have to actually be able to do that, because it says it can be done. So you can assume, and this might come up in the exam, they say this can be written in this form. And you go, okay, fair enough, I'll take your word for it. But notice it says compare the efficiency of these two. So we'd already, I think, worked out that this had 6 multiplications and it had 3 additions. So I'm just wondering if that is the same as that, what's this got? Now, imagine I had my 23 again, and I put this in, I'd have 4 times 23. Plus a 5. And I'd times that by the 23, and I'd add a 6. And I'd times that by the 23 and take away a 7. So what's that got? It's got 1, 2. Now this has only got 3 multiplications and 3 additions, I think. 1, 2, 3 additions. So that looks a much more effective way of multiplying that out. Now, it might not matter if you're only doing it yourself, but if you was getting a computer program to do this a million times, perhaps it does matter how quick it does it, because you don't want people waiting. So these kind of things matter if you're doing lots of them and they're complicated. And it does say there that the nested form is better. So look, if I was doing this in class, I'd be saying to you, now let's have a look at this exercise. So I hope that makes you understand what time and order means.